this is the first part of a mini course on differential privacy and statistics, which was put together by 3 people, Sesa Slavkovic, who's going to speak now, and Vishesh Karwa, who unfortunately couldn't make it, and Gautam Kamath, who's speaking in the afternoon. And so we're going to start with a talk by Sesa giving us sort of a statistician's perspective on statistical inference in privacy.
Thanks. Okay, thank you, John. It's great to be here. So just to reiterate, so basically in the next block there will be roughly 3 talks. So the first one, Vishesh couldn't be here, so I'm trying to relay, or I guess give you a sense of his and my perspectives as statisticians on statistical inference and privacy. The second talk will be by Gautam on computer science perspective on inference and privacy, and he will give a few specific examples. And then the last talk will focus a little bit more on applications, and we'll talk about synthetic data. And Rachel Cummings, who is here, has graciously agreed to help us out and give a computer science perspective specifically on synthetic data. Okay. So my talk, I will try to give you a bit of I guess, a high-level overview or some sense of how some of us in statistics community think about statistical inference given the privacy constraints. And I think what motivates many of us to work on this problem is what Cynthia Dwork and John most recently coined the Feinberg Problem. And I will just quote what they said the Feinberg Problem is. It says, how to give unfettered, unrestricted data access to trusted and well-intentioned analyst and permit him to safely publish his, and I added here word valid findings. And that idea goes back to beginnings of some ideas of differential privacy, and I want to take a moment to reflect on this. So first, Journal of Privacy Confidentiality has just relaunched in December with an issue in special honor of Steve Feinberg. For those who did not know Steve, he was a famous statistician. He passed in December of 2016, and he was one of the main actors and a driving force, really, in bringing computer scientists and statisticians together in trying to address data privacy problems. And I was lucky that actually in 2003, when Cynthia Dwork presented some of the initial ideas on formal privacy, differential privacy, Carnegie Mellon, I was there, and I remember Steve saying right away after she finished her presentation, saying something to the extent, well, you just threw all the utility down the toilet, okay? And so, but Steve was an optimist and a visionary from my perspective, and along with Cynthia and Kobe and Adam was there at the time as well. There was a workshop that was organized in Bertinoro, Italy in 2005, very much like this workshop. The intent was to bring the computer scientists, statisticians, and practitioners together. And for some of you who were there, there's a story that has been retold many times. The workshop almost broke down on the second day. So no bad juju here. We're on the second day, so hopefully no going down that path here. So what happened? Well, statisticians thought that cryptographers were paranoid. We couldn't really, which is true, we couldn't really understand this excessive worry about auxiliary information and exceptionally strong adversary. On the other hand, the cryptographers are really frustrated by ad hocness, that statisticians brought to the table. An ad hocness in the sense that they wanted more formal privacy definitions, both in terms of a risk and utility loss for statistical inference. So fast forward 15 years plus, or around 15 years, depending from which point you're looking at. Here we are again, a diverse audience, and we're still discussing and trying to figure out, discussing the same problem and trying to figure out how we can find a common language and the common ground. But we did come along, and there have been many, many improvements and movements in this direction. Okay? And so I will hopefully give you some sense of that, that I feel for me as a statistician, some of the notions that I was introduced to back in 2005 have moved me in a particular direction in thinking about a data privacy problem in statistical, when it comes to statistical databases. So the way that I want to think about it, and I think about the Feinberg problem, is that our ultimate goal is to share data under now rigorous privacy guarantees. So rigor is coming now, if you think from formal privacy or differential privacy perspectives. But we also want to maintain data utility for statistical inference, and I will shortly define what I mean by statistical inference. And why is this important? Well, you know, as a statistician, as a practitioner, you want to encourage reproducibility, you want to encourage good science. We typically want to combine multiple data sources, and we want to make data accessible and available to users that otherwise they would not have access to the data. Okay? In this process, there's this risk-utility trade-off, and specifically, I'm referring to disclosure risk, and for some of us in statistics community, we often like to think about framework of differential privacy or differential privacy perhaps as a way to specifically define disclosure risk, as a measure of disclosure risk. Okay? And that requires additional non-trivial amount of noise. We heard that yesterday from a number of talks. And this is the same idea that has existed in statistical disclosure limitation literature since the 60s, which said you need to introduce additional bias and variance into the data. Okay? However, how you formalize that, that's what the difference has been for the past, 50 years, 60 years in statistics community versus what computer scientists and particularly cryptographers has brought to the table in making us think more rigorously about the problem and these definitions. Okay? Oh, that I didn't expect. Okay. And then the data utility basically asks the question, well, what are the data useful for, and more specifically, can we actually infer valid statistical inferences from these noisy data? Because we know we're manipulating them and we're not working with the original data that we're used to if I'm a real practitioner and I'm a survey researcher, right? So, so this is, the assumptions are that we're gonna assume that we have some rigorous privacy models. We're adding non-trivial amount of randomness, and we're interested in understanding what are the implications for statistical inference. So the talk will focus on how can we perform valid inference under the constraints of formal privacy models, and how can we design the optimal differential private mechanism and inference procedures, and hopefully I'll be able to explain what I mean by optimal. And I'll try to provide two points of view from a theoretical statistician's and an applied statistician point of view. Okay, and this is rough. I mean, I consider myself both, but I really consider myself more a methodologist rather than theoretical statistician. Anyhow, so what is statistical inference? So no privacy. I don't care if there are any privacy constraints. What do we do in statistics? The main objective in statistics is that you're given some observed outcomes, some observed data, you want to infer what the data generating process is. Okay? So if I have set of records that come from some distribution P that could be a normal distribution. Let's say we assume that income comes from a normal distribution. Typically, I observe a random sample of individuals from my underlying population, but my inference is all about the characteristics of the underlying population. Okay? So one way to make that statistical inference is to say I want to find my best guess estimate of what the mean unknown, what the mean income is in that population. Okay? Going back to the talk about statistical learning, from my perspective, statistical learning, machine learning is also statistical inference. It's just a statistical inference that has a different objective in mind. Okay? The focus is more on prediction, but there, you can think of many different ways of how to what the inference would be depending on the context that you're working with. Okay? Most statistical inference tasks can be identified as three types: estimation, and we talk about point estimation, confidence intervals, and hypothesis testing. These are tools that any, especially applied researcher or statistician will work with. I will focus on some of those in the talk. Okay. So then the next question is also how to construct optimal estimators, and I'll get to that in a bit. Okay. So I'm interested about the quantities at the population level. I don't see really my population. What I see is a random sample, and I use that random sample to figure out my best guess about quantity of interest in my population, okay? And some variation around that best guess, okay? Now, what happens when we introduce privacy constraints? I said earlier, we are saying that we're now going to add some additional randomness. So I still have that random sample. So I ran a survey of 100 students who are applying to various Berkeley graduate programs at Berkeley. It's a graduate admissions time right now, right? And I add some kind of noise through some privacy mechanism. This privacy mechanism could be differential under the framework of differential privacy, could be something totally different, such as synthetic data without differential privacy. Okay? It's a privacy mechanism. Okay? So, and I'm saying here, from my perspective, a privacy mechanism then is simply is a family of conditional probability distributions. Okay? And that's what I'm denoting is Qy given x1 up to xn. So now the private sample space that I actually work with and that I actually observe. So I don't really observe this space any longer. If I'm the user, I actually observe this space. Now, instead of making inferences from this sample to the population, I need to make inference from the private sample to the population because I'm still interested in figuring out the same characteristic. I'm still interested in knowing what is the true average income in this population of interest. Okay? Yes?
So just to clarify here, by user you mean the statistical query or whatever, not the people who are those stick figures there?
Correct. By user, yes, correct. By user I mean those data analysts. Okay? Although one of them could be a data analyst. Yes?
So here are you assuming that this Y itself is of the same type as a data set, or could Y be actually a private estimate of theta itself?
So Y could be it could be an estimator from the data. It could be a data themselves, like a synthetic data, or another random sample. That's a great question. Yes. So it could be some measure, could be some statistic, right? A noisy statistic, or could be data themselves. That we introduce some additional noise, bias and variance too, okay? And again, I'm trying to figure out the privatized estimator. So this is what I said, this is the goal. I still want to now estimate the same quantity of interest in the underlying population, subject now that I have this privacy model, okay? So here, just to be clear, F is a set of all conditional distribution that satisfies, let's say, differential privacy, because that's what I'm going to work with for the rest of the talk. Okay. So we have seen this definition of differential privacy yesterday. I don't think I need to go through this again. So I'm assuming the same definition. So this is the conditional distribution. This is kind of the mechanism, just a different labeling. And the epsilon is the measure of information leakage, right? What I do want to bring out is that I think for many statisticians, we found the following interpretation of differential privacy quite useful. Oh, that's not me, okay. I was like, what am I doing? So Wasserman and Zhu, Larry Wasserman and Zhu, and they had a paper in 2010 in JASA where they kind of outlined their version of statistical framework for differential privacy. And basically what they show is that one way to interpret differential privacy is that if you're interested in testing if user is part of the database or not, right? This is a hypothesis test. You basically have no power, statistical power to do this, okay? Because the power is bounded by alpha e to the epsilon. Epsilon is your privacy parameter, and alpha is the type 1 error. Typically, let's say 5%. In most cases, it could be something else. You can figure out what it is. So that's a very low value, and I think that type of interpretation for a lot of statisticians makes sense. Right? And I think part of the objective of this workshop is for us to figure out how we can communicate to each other about some of these basic concepts, okay? Yes?
Can I ask a question about
this? Yes.
I'm just curious, this is sort of a perception psychology type question.
Yes.
If that bound on the power had the form alpha plus epsilon, do you think that it would be equally convincing to the community? Not to you specifically, but to the community at large? Like, does the multiplicative form of the bound, do you think that registers as important?
Well, I mean, if the epsilon is very small, which is what we aim for, then it's right.
Let's say 0.01.
That's a good question. I mean, if.
So it's like the question: what is very small alpha?
Yeah, what is a small? I mean, but I think this is what I'm thinking about. I mean, here we have seen applications where epsilon is very big, right? So then
But even there's a sense in which epsilon equals 1 in 100 is also kind of big if alpha itself is super small.
Small, right? Yeah.
Depending on the test you're employing. Right?
Well, I think the reason why this is useful is because of the way that the original definition is defined, right? So, but you're asking me why we're finding.
It's entirely a question about like perception in the statistical community.
Yeah.
If the form of that bound had been slightly different, would anybody care? I mean, but like, is there?
If I think, well, okay, so so yes, let me say yes and no. I think a practitioner, right, to whom you're saying that the power of identifying that person is extremely low, wouldn't care. I think for theoretical statisticians, if depending what bounds you need to derive, like if we talk about minimax bounds and other suboptimal properties, maybe you would care what the form is. Does that help?
Yeah, that's fine. I mean, this is I think an interesting discussion there, but no.
I mean, I'm not sure that. Yeah.
So as a statistician, the first time I saw it, my eye did not go to the multiplicative form. It was the E.
Right.
It was like, why the hell is there an E? But it's not alpha plus delta or alpha times delta. I'm not sure I would have cared that much about that difference.
Right, whereas, I mean, there are mechanisms that are kind of clearly horrible that satisfy the additive bound, but not the multiplicative form, like just picking a random person and publishing their data in the clear. Okay, maybe not completely horrible. Anyway, sorry, I don't want to decide.
Okay, well, two additional statisticians in the room, it's like, Doesn't matter. Okay. So the other properties that are nice, we already heard about this. I'm not going to go into it, just so that we are aware of this and it is appreciated. The composition, it's a great thing because it says we can have multiple releases and we understand how to break down that potential privacy budget given the multiple releases. Robustness to post-processing is good. Again, this idea that you can quantify the privacy budget. Of course, there's a whole separate question of what the privacy budget ought to be. And transparency is really, really important. This is something that the fact that differentially private mechanisms are transparent throughout. You know exactly what type of noise you're adding and when you're adding. That is actually also very important for statistical inference. And I have to say that many of statistical methods that were developed up to now, or even some who are still in use, in many of the agencies, they clearly lack transparency. So Kobe mentioned yesterday swapping, and he said, well, we know they swap, but we don't know what the percentage of swapping is. Or you perturb the records, you don't know what the perturbation is, or you hide the cells. We know statistically that you're hiding them, you're going to get missing data. They're not missing at random, but you have no idea what the missing mechanism is. That is really going to affect your inference. So this is for statisticians in the audience, right? So this transparency is really important, okay? So basically, if we're going to work with differential privacy and we add in this additional randomness, we need to think about how do we still maintain valid inference, and does that mean that we have to modify the existing methods? Do we have to come up with new methods? Because ignoring the noise will lead to invalid inferences, and particularly in finite samples. Okay, and so I'm going to use one simple example to demonstrate this, and I think Gautam will spend quite a bit more time specifically in the hypothesis testing, showing some differences, how this affects the inferences. So why confidence intervals? So I said earlier that basically the three key inferential tools that we all think in statistics about and start from: point estimation, confidence intervals, and hypothesis testing. So confidence intervals, in addition to the point estimator, which just gives you the best guess of the quantity of interest, we are always interested in capturing uncertainty about the quantity of interest, right? So confidence interval will quantify uncertainty in parameters. And confidence intervals, that's one way of quantifying that uncertainty. They're building blocks for almost all of our methods that we develop, being parametric, non-parametric, linear regression, and causal inference, if you think about the applications. One example in statistical disclosure limitation, of course, where confidence intervals are discussed a lot, where with this idea of verification servers. So the idea is that user doesn't have access to the original data. User has access to the data analyst, I should say. Data analyst has access to, let's say, some synthetic data or some perturbed data. But they want to make sure that the results they're getting correspond to what they would have got if they had access to the original data. So verification server will basically then spit out the output and say, here is the confidence interval and how it overlaps on the original data versus the synthetic data or the manipulated data. Okay? And of course, it's been shown that giving those type of confidence intervals compromise privacy. And there's work that I didn't cite here most recently by people at Duke who are looking also to provide, for example, differentially private outputs from the verification servers, or they're looking at those type of problems. Okay? So can we do valid confidence interval under the constraints of differential privacy?
Can you define what is confidential level?
What is the
confidential interval?
Confidence interval. I will in a minute. Okay. So, I'm not going to go too much into detail. So I'm going to assume that data, random sample, let's say from a normal distribution, centered at mean mu and variance sigma squared. I'm going to assume the sigma squared is known. This is like the simplest inference problem in statistics. And I will also assume that the mean has some known range. Okay, the parameter is unknown range, sorry, but it's bounded. And we want to construct 1 minus alpha level epsilon dp confidence interval from mu. Okay, so what does it mean in terms of non-privacy? So without privacy, the best interval, it will be centered at the best guess estimate of your mu, so in this case, like sample mean, plus or minus some variability that comes from the sample, multiplied by this value here, z with the subscript alpha half, and that is related to this coverage that you want to have of this interval. So alpha, the typical example, alpha is 5%, right? So here I'm going to look at values of z from the standard normal distribution. I'm looking at the probability that z is greater than some value, and that has to be equal to 0.25, or the probability is here in the edges, okay? So this is my confidence interval on that normal distribution, right? Okay? And so the length of the interval here is 2 sigma divided by square root of n times this is z alpha half. 95% confidence interval is the most common one. I can have a 90% confidence interval. I can have 99% confidence interval. This is all about how confident you want to be about your estimation, or how much error you're willing to produce. Type 1 and type 2 errors, false positives and false negatives, okay? So what we want is to produce the honest and smallest possible differentially private interval in a minimax sense. So what do I mean smallest? Well, I want to have, for every n, I want my coverage to be 1 minus alpha. Okay, so that's really what I want. And smallest is because I want to have the best or the soundest inference that I can in this particular setting, okay? So can we do something simple? Okay? So I have the data, I have here the bound on the data, that's required. I'm going to use the Laplace mechanism. So I didn't define the Laplace mechanism, but briefly here I will. So you add noise from the Laplace distribution that is proportional to the global sensitivity. And in this case, I'm going to truncate data x1 up to xn, and they lie in this bounded data space. And I'm getting here t1 to tn, so these are truncated values, right, from some truncated space. So I'm going to compute truncated mean. So instead of x bar, which is using all the data without any truncation, now I'm computing the truncated mean. I have the global sensitivity of the truncated mean 2b divided by n. Okay? And I'm going to add noise to this trimmed mean, z, where z is the Laplace noise with mean 0 and the standard deviation 2 times global sensitivity divided by epsilon. Okay? And I'm going to output that noisy mean. Okay? So this is taking an optimal procedure in statistics and trying to make it in a simple way differentially private. So how does it work and what does it do? Of course, how do I assess, is this a good thing to do? Well, I want to also use these confidence intervals perhaps to do hypothesis testing. And I'm interested in also understanding what is the sampling distribution of y bar. So there are 3 approaches here. I'm going to consider 3 types of sampling distributions. I'm going to ignore the noise. So I'm going to take the y bar and pretend like this is the original, like it came from the original sample. I'm going to incorporate the noise, the variance of the noise in the y bar, so the variance from the noise from the Laplace mechanism. And then I'm going to derive also an approximate sampling distribution of y bar. So I'm going to do an additional approximation. Okay? So I'm going to look at these 3 distributions. So this is a distribution, a sampling distribution of the sample mean, ignoring the noise. So notice the values here on the x-axis. Here's the sampling distribution of the noisy y bar, sampling mean, when we actually take into consideration that the noise was added from Laplace distribution. So see the effect here that I am definitely changing the variance, right? And then I can also use, I can do a convolution. Basically, I can use a normal Laplace approximation. So here, I've approximated Laplace by normal. Here, I'm actually doing the full-on convolution on normal and Laplace. So even, I'm still calling it approximation. And I get a slightly a different variance, okay? If I want to do hypothesis testing, I'm going to use the sampling distribution for hypothesis testing. So let's say that I'm interested in knowing that mu is equal to 0. And I can compute p-values that I'm sampling here. Yes?
Can you go back? And
yes.
Maybe, or even one more slide back. Like, 3 approaches, and your goal is to do what? To produce the confidence interval that is the one that holds the actual mean with probability 1 minus alpha.
Yes.
Where now alpha.
I want honest and smallest possible interval, right? So honest is I want the coverage 1 minus alpha for all possible n's.
And for all mu.
And for all mu, yes.
Or between minus b and b or something like that.
Okay.
But I'm not saying this is the good thing to do. Like, I'm not saying this is the procedure to do it.
Well, those 3, I'm not sure I even understand why all these 3 are, well, the first one, why is it honest, and the second...
They are not. So my goal is that this is what I want. So I'm starting and saying, I'm going to take a naive approach here, because I don't know any better. Because I have a non-private optimal procedure that I know how to construct a confidence interval, right? So now what I want to do, I know I'm adding noise, and the noise has been added. So let me explain why I'm showing you this. Because so let me back up. In statistical disclosure limitation, we've been producing perturbed or noisy outputs for a very long time. I should say agencies have been doing this for a very long time. And they actually did add noise to data, okay? And they were sharing these with users. In most situations, and not most, probably in all situations, user always treated those data as the original data, okay? So that's this. From my perspective, adding noise from Laplace distribution or Gaussian or something else, I'm adding noise, right, to the statistic. Of course, here it's under more well-designed mechanism, but I'm adding noise. If I'm an outside user, I'm very naive, I'm going to take that summary value, and I don't know any better. I'm just going to use it believing that's my original data. Does it make sense? I mean, this is important, right? Because there are a lot of people, I mean, we've been doing this for many years, and specifically, I want to demonstrate that with differential privacy at least, we have a way to account for this in a right way that will actually give us the right confidence interval, right?
And so I guess most of the time your mu is not going to be in the interval.
Well, this is going to be, I'll explain. Yeah, this is going to be, in this particular case, I'm actually going to get a very short interval, right? So it's going to be a problem. With some other cases, I'm actually going to get something that's extremely wide, which is also not good for inference purposes. Okay. So let me get to that. I was going to make the point with this. Is it clear what I was doing here?
It's not clear to me why the left option is. I understand that naive users may think this way.
Yes.
But it's not clear to me why this is part of the statistical analysis. I mean, you're not naive users.
I am not a naive user, but I am not your only audience. I'm not your only customer, right? Many practitioners out there, data users, they're your customers, or our customers, I should say. So my point is that I'm showing this, first of all, to demonstrate that this is a bad thing to do, to ignore the noise, right? And to say that we actually need to relay this message to the users, because a lot of questions that we're getting from the users these days, they're saying, they're hearing about changes at the census that are happening, right? and saying, oh, census is going to produce synthetic data. Census is going to produce differentially private outcomes, right? The statistics. And they're freaking out and they're saying, you're going to ruin all my inference, right? Going back to Steve's, the utility is going down the drain. Because they don't understand how to account for that extra randomness. And that actually we can account for that extra randomness. So there's an educational aspect here that we need to reach out to a particular audience, right? Again, going back to, I don't know if it's easier to understand. I perturb the data, or I suppress the cells in a table, right? And I gave you a table with what we call Swiss cheese, right? These data are not missing and random. But the users analyzing this data have been treating them as missing and random. This is the same thing. They basically are completely ignoring the noise mechanism, and that is wrong. And this has not gone away. This is still a problem, right? So I think that's why I was trying to bring this up. Any other questions?
I mean, it's motivated by the approach that when n goes to infinity, it should swallow the noise from differential privacy. Only, I guess what you're showing is that.
Well, okay, here we go. So yes, and I'm interested in finite sample inferences, right? And what does it mean n goes to infinity? How large does that n need to be, right? That's an important question which you guys are looking from sample complexity. We are also looking at that question, right? Trying to come up with these like multiplying factors to adjust for this noise. So here I thought through these p-values, this is maybe more clear. So I'm producing p-values and assuming the null distribution is true, given the null distribution is true, the p-value should have a uniform distribution. Okay? So here is the non-private case. These vary by sample size. 10, right? 10 sample size, and not 10 billion, 100,000, 10,000, right? And so forth. So looks pretty good, reasonably uniform, right?
What you want, the box plot is showing quartiles, right? So you want it to line up with 0.25 and 0.75.
Yeah. Yeah. Okay. And I want to also to show that this is symmetric. It's roughly this is all uniform here. It's looking great. Okay. So what's happening here? This is the one where you naively ignore the noise. This is what you were asking me about. Like so.
There's no noise, right?
First one, there's no noise. This is the original one, right? But I'm resampling here, right? This is a simulation, so there is some randomness from sampling that I'm doing, right? Okay. So here is where I'm ignoring completely the Laplace mechanism. I'm ignoring the noise. This is horrible, right? And speaking of n goes to infinity, I mean, here is n. What is it? I'm looking at 100,000. I'm still not doing that well, right? And this is the simplest problem in statistics, yeah.
So the way that you're getting these p-values, you're assuming you know this sigma.
Yes.
So this is why this has been pushed to the extremes.
Yes. Yes. I'm assuming, again, the whole problem is the simplest possible problem. It's being pushed to extremes because I'm assuming I know sigma. Yeah. Okay. When we don't know sigma, then these things can be addressed as well, but I was trying to use the simplest example. Now, here is where you do normal approximation, normal Laplace, we're starting to do better, but these are basically the cases where now we're explicitly try to account for the noise that the mechanism introduced to the original data. Okay. And so we are doing better. So it's important to have a transparent mechanism to be able to account for the bias and variance that we're introducing to the original data if you want to get the right inference.
Just so I make sure.
Yes.
The normal is better than normal Laplace, right? I'm understanding this correctly or not?
Normal Laplace, yeah, this is the convolution, and here I'm approximating Laplace by the normal, so it's kind of normal. That's what I mean by approximation.
You want them to hit the 25 and 75
20.
close
Right, so
as
it
possible,
doesn't-
so the
so
normal
your
Laplace
third-
does.
So your third
Yes.
better than maybe I'm not understanding.
Yeah.
You want to be between the points of
Yeah, 0.25, 0.75. Yes, he did do better. Because we actually are accounting, we are accounting for some additional noise in the right way. Okay? So it's kind of like taking care of some also randomness here. Okay? So the problem is, ignoring noise can lead to invalid tests, invalid inference. So in the first case, I'm getting narrow confidence intervals, right? So will not lead to the good inference. So let me, I think I need to probably, I'm looking at the time. So basically what we're talking about is that one solution here is that we need to incorporate the distribution of the noise into the procedure that we're doing if you want to get the right inference. And there's a new paper by Wang et al. This is work from Daniel Kiefer and actually Vishesh. They actually provide some results and asymptotic arguments as to when the asymptotics kick in and when it's actually sufficient to do just asymptotic inference. Okay, so this paper also just came out in this issue in JPC. Okay. Now, variance of noise added is linear to B, and if you remember, B is the range on the data, right? And so this is the standard error of that Laplace random variable that we're adding noise to, and this is the standard deviation from the sample statistics, just from the random sample. Okay, so B is the bound on the data, right? So here the point that we want to make is the choice of B is also crucial. Okay, so if you take small b, you're going to truncate and you're going to add bias. If you take a very large b, so you really, take a wide range for your data, then you're going to add a lot of noise and you're going to increase the variance. Okay. And in finite samples, that can be very, very important because there are examples that I think Vishesh, in his work with Salil, I don't recall if they have this in the paper, but he said that in some cases, given these choices, the confidence interval would be like 16 times larger than what really it's supposed to be. To a practitioner, right, that's a useless confidence interval. I can't make any inference if that is too wide either. Yes?
But I mean, isn't B based on the data? How can you choose B? I mean, if your data is ages, then, it's roughly going to be, I guess, 1 to 100 or something like that. But you can't say I only want to have it be 25 to 75, right?
So that, I think that's a separate question. I mean, the one thing also the differential privacy assumes that you actually have to have some boundedness on the data. So in some cases, you can also transform the data, so it gives you some natural bound. In some cases, given, I guess, some prior information, you can decide what the bound is, but you will have to account for that as well in a differentially private way if you want a whole procedure to be differentially private.
So maybe just to make sure this is clear, right? The B parameter here is supplied by the user.
Yeah.
Some belief. So if you know it's an A,
yes.
It's not data dependent. Like this wouldn't be private if B is like the actual range of the data.
But there are other approaches.
There are other approaches where you could, yes. But again, this is the simplest case. This is the B is provided. Thanks, Claire. Okay. So I won't go into this. You can read a paper by Vishesh and Wadhan. So they're basically saying we have a way of figuring out what a nearly optimal confidence interval is. Okay, and they're limiting the dependence on the standard deviation of the noise on B, and they make no assumption of the range of the data also in their procedure, which is important. And they basically have minimax lower bounds on the length of the intervals. So Gotnam is maybe going to mention some of this, so I'm not going to go into the details on this. Okay. So interval estimation with non-variance, and in essence, I think what they do, it's a two-step algorithm. So now they're going to look actually the range of mu instead of looking at the range of data. But again, that's Gautam is going to, I think, talk about this, so I don't need to get into details on that. I'm just going to show here that what's important is that this is the length of the confidence interval, the differentially private confidence interval, and you see a clear understanding of what comes from the random sample and what comes from the mechanism. Very, very, very important. Okay? This is really the only thing I want to say about this slide. Very important for the inference to understand how to separate these things basically in order to model the noise that we get from the intervals. Okay? So estimating a confidence interval, so ignoring the noise leads to invalid coverage. That's basically what the sampling distributions and the p-values were supposed to show. And if you're very careful and you can define well what the privacy mechanism is and what the normal distribution, or what the distribution is, in our case a normal distribution, then we can account for that in the right way. And so this idea, how to perform valid inference, kind of generalizes. Okay? So what really want to do is we want to treat if gamma here is basically your Q is the privacy mechanism and gamma is the parameter of the privacy mechanism, we want to treat it as a nuisance parameter. Okay? So in statistical inference, the problem that I didn't show, I assumed mu is a parameter we're trying to make inference about. Sigma I assumed is known. Often sigma is not known. So in many cases, if I'm not interested in sigma, I can treat it as a nuisance parameter, and I will find ways of integrating it out or doing something with it. Okay, so this is the same thing so this is one of the principles or ideas from statistics. So I want to integrate this mechanism out. So I'm going to now work with this marginal likelihood, and it's this distribution that I'm going to use to find my point estimates, to do the confidence intervals, to do hypothesis testing. Okay. And this is different from my P, my probability distribution that I begin with, from this one, okay? So instead of working with this one to do my inference, now this is the distribution that I'm working with to do my inference. Because in that, I accounted for the mechanism noise.
How is this different from what you were talking about? I'm confused.
It's not. This is generalization. Okay, I was trying to give an example of through the confidence intervals. Now I'm saying this generalizes. I don't care what this privacy mechanism is, right? It will work for anything. Like this is a basic principle, basic idea. Okay? As long as I understand the parameters of the privacy mechanism.
Doesn't this introduce some sort of computational issues?
Yes, I will get to that. Yeah. Okay, great question. Right here. Okay. So mu is an important object for valid inference in certain quantifications, right? So it's a marginal likelihood, okay? So let me just say, with that, this is what I said earlier, I can compute the estimates, I can compute the posterior distribution, I can generate the synthetic data from this distribution. There are many, many tasks I can do with this, okay? Compute confidence interval, but marginal likelihood is often intractable. This is what you are referring to. So, of course, then we have to do some approximation to the marginal likelihood. This is still very much an open problem from our perspective. We have worked on it in a couple of problems. Some other people have worked on it. Here are a couple of references. But we need to do better. But from our perspective, there are, again, two principal approaches to attack this. One is to look at from the measurement error modeling approach, okay? So this is often applicable when there is a sufficient statistic, okay, in your model. If there are questions about what sufficient statistic is, I can explain in a bit. If it's of interest, I want to get through some of the slides. The other one is to find a surrogate or missing data likelihood. Okay, so approximate M by some surrogate M. And this is where some MCMC or variational inference or bootstrap type methods come into play. So the whole point is that we're trying to find the best approximation to this marginal likelihood. Can we get the good final sample performances? This is finite sample performance in this case. This is also a question. It's well known that asymptotia is nice, but again, here I don't know if I talked to Frauke. Many of her colleagues will work with a random sample of 500, 1,000. If I'm in clinical trial, it could be 30 people. Right? Those are very different numbers from looking at extremely large numbers here. And this is basically a ratio of the private and non-private confidence intervals that Vishesh produced. And basically just showing you, without going into details here, that very large sample sizes. This is for trimmed mean, trimmed asymptotic means in the median boots. It takes a while for the asymptotics actually in this particular case to kick in. And in many real applications, the sample size is much smaller. Okay. So, so that's one way we're thinking about what are some of the principles that we should be, statistical principles that we can use to do some valid statistical inference under privacy constraints. Then the second question is, can we design optimally differentially private mechanisms and inference procedures? Okay. So we saw that with the add Laplace noise, that was suboptimal. So you you can potentially add less noise by adding a differentially private estimator or range of the data. We want mechanism that was designed perhaps to optimize over all possible DP mechanisms. So we want some kind of uniformly most powerful mechanisms or outcomes. Okay, and related to this. There is something that, of course, in the binomial case, a student of mine and I have worked on, so we derive uniformly most powerful differentially private binomial tests and p-values, so this is over all mechanisms. And we also have extensions for confidence intervals and a couple of other things. And I think Gautam is also going to bring that up, okay? So as a statistician, how do we think about how do we design an optimal estimator? Again, without privacy, and this is a very simplified view, theta is the true parameter of interest. Theta hat is some kind of estimator of that. This is a loss function that basically measures some distance between the theta and the theta hat. Risk is the average loss function over that distribution, probability distribution P. We also assume we have some kind of model, which is a collection of all probability distributions. And so we need a single summary to now compare these risks. And two most common ways that we do this in statistics is to find a minimax estimator or Bayes estimator in order to figure out what is the best estimator. So this kind of gives you a sense of how do statisticians think about devising best estimators, or what I call them designing best estimators. And I think some of the same principles should hold even if you have privacy constraints, okay? What is the loss function? I think many of you are familiar. The point I want to bring out here is that I can have a mean squared loss, right? In that case, the risk is the mean square error. In the hypothesis testing, my loss could be some trade-off between type 1 and type 2 error. Okay? In set estimation, the loss could be the length of the confidence intervals. So there are many different loss functions that we consider. How and when do we consider which loss function? Also depends on the problem, right? So prediction or point estimation, doing mean square loss is probably good. If I think about causal inference or combining many estimates, like values across many clinical trials, there, having unbiased estimators is really important. So there, I maybe want to think about a slightly different loss function that I want to consider rather than just using the mean square error. Okay?
Can you say a word about why unbiasedness is so important?
Okay. Why is it important at this point in this case? Because you have many different sources and you have to average over all of them, and it's hard to kind of know if they're all unbiased, how to account for that. So
okay,
you aim for.
I guess I see it with combining many estimators.
Yes.
My question was really about causal inference.
In causal inference, you may also have multiple estimators, depending on the problem, because you have the counterfactuals, right? What would have, so in causal inference, they typically care about unbiased estimators. So, and I mean, yeah, I don't know if I can take a good example right now, okay? Ask me after the talk, maybe think about it. And so that's the point here. I mean, this is just a repeat. So in this case, we can work with this marginal likelihood. And again, the point here now is that the risk is not to respect to P anymore. The risk now is with respect to this marginal likelihood that we have derived. Okay. But we can still use the same tools. It's just a different space which we're working with. Okay. I'm going to skip this. My point, this is going back to the earlier point that it could be an estimator, it could be synthetic data. There's really not much difference here. we can design differentially private mechanism or any private mechanism, or sometimes the private mechanism is given to us. So if I want to design the private mechanism, I can think about, give me a loss function, give me the family of probability distribution, give me family of differentially private mechanisms or conditional distributions that satisfy some differential privacy. What is the best pairing of Q and theta hat? That's I am designing. Okay? Observational, I can say, hey, John has already produced a differentially private, Adam has already produced a differentially private mechanism to release a median. Okay?
Just put lower bounds.
Well, because you were talking about the median yesterday, right? So now, given that you gave me that noisy median, right, I want to find the best theta hat, which is what we were talking about. And you can mix these two, design and observational setting. Here, the Q could be differentially private synthetic data. And I can do many different things with that. Okay. So there are some connections to algorithm design, design of experiments and surveys. Here, thinking about a priori what we want to do in designing things. Back in 2009, and actually we had a workshop at IPEM in 2010, I talked about these factors for adjusting sample sizes, and I typically talked about a clinical trial, and I said, listen, you want to design a clinical trial, you know typically what type of hypothesis you want to test. I can introduce privacy into the design process at the onset. I don't have to wait till the end to introduce the privacy, right? And I remember at that time, you know, I was talking about sample sizes of 10 and 20 and 30, and Cynthia Dwork said, wait, that's not what we're doing. We need data sizes in millions, right? But we are here. We're addressing these type of problems. So that's, I think, a great leap. It's very important, okay? Both views will be useful. Again, agencies, census is designing some differentially private mechanisms right now. So these values are, these issues are important, okay? Oh, and here the question is, what should Q be designed for? What class of P? What class of loss functions? I hate to say it. Maybe this is better phrased now than it was in 2005. But we had the same type of conversations and the questions in 2005, basically. If you recall the workshop. We were still asking, who are we designing for? What are we designing for? What are the models that people want to fit? And you keep asking us, like, how do you know? And we're back at this again, and in some cases you have to think a priori, what are the potential uses of this data? I think it's really hard to get away from this, okay? So differential privacy mechanism introduce additional noise. We want valid inferences. We need to model that additional randomness. We claim that basic principles for measurement error, literature, and missing data mechanisms in literature and statistics can be used in this case. You know, this is obvious at this point. The simple Laplace mechanism may not be optimal in many cases. And we do have to actually think very carefully about designing algorithms and inference procedures for each inference tasks, especially if you're thinking about finite sample performance, okay? Great. Is this going to work? Give me a second, let me wrap up, and then you can ask a question if you don't mind. More realistic picture. I had statistical model, random sampling, but then there's always something else, right? Data collection, cleaning, exploratory analysis, model fitting, model checking, interpretation of the results, right? Here's your superpopulation, finite population, random sample. This is where all kinds of measurement errors and missing data issues come in. So an applied statistician view, I care about data quality, right? Junk in, junk out. So I really need to make sure my data have some integrity, okay? So I worry about measurement error, missing values, sample biases, structural zeros, and I suspect that Frauke will talk about some of these issues, okay? We still really do not know how to address many of these. There's some work on structural zeros, etc., but in general, I think we're pretty far away from addressing these problems. A lot of effort goes into modeling sources of uncertainty to get valid inference, especially for I would say, survey statisticians. Model estimation, Every model estimation, we always think about parameter estimation, hypothesis, confidence intervals, so you really could not get away from that. Model means specifications, right? I assumed my normal model was the correct model, right? I could be wrong. We typically assume model is never true, only approximations, right? We know the census is dealing with a lot of hierarchical data these days and issues that come from that, model checking, model selections, etc. So how do we perform all of these in some kind of privacy-preserving way? That's a very general, very open question, but pick any of these highlighted words, and there's a problem to be worked on. Okay? Optimal allocation of epsilon. So that's a whole other thing. So I'm just going to wrap up with this last slide. So in ideal world, we want to give access to data to trusted and well-intentioned analysts and permit him to safely publish valid findings. So I want valid confidence intervals, point estimates. I want valid hypothesis tests, okay? At least. Okay? So that I'm going to, I guess I'm over my 5 minutes. Okay? Thanks. Question?
In the latter part, you talk about point estimation. Like well, before that, you're given all these min-max bounds and but here, for example, so confidence interval is not even. Is it implicitly here in these equations or not here?
So in
Is it completely disjoint thing from the confidence interval you had in your first part of the talk?
No, this is, so I've used the confidence interval as an example of thinking about how we can do valid inference under privacy constraints and how we can potentially design valid mechanisms, right? So Salil, tell him I rename him. Salil and Vishesh have designed a differentially private mechanism that gives nearly optimal confidence intervals, right? That's a design question. Okay? And so, of course, that fits in here. They had some loss function in mind, and their loss function was, so when I say here, you specify a loss, you specify a probability, a family probability distribution, you specify a family of conditional distribution of the privacy mechanisms. And the loss there for them, they wanted the coverage of the confidence interval to be smallest. There was a specific loss that I defined on one of the slides earlier, right? So it fits. My point is that what we're trying to say here is that this is from our perspective, this is a more general framework of addressing many of these problems. And I only used confidence interval to demonstrate it, but I can talk about uniformly most powerful binomial tests that Jordan and I have done, right, which basically does the same thing. We're designing this with a very specific criteria in mind. We want the uniformly most powerful test. That's important in statistics. It's a classical result. It's a Neyman Pearson result. So we want to see, can we have that same result under privacy constraints? And we work with differential privacy. And I think this is another way that you can convince especially applied statisticians, because they're, or practitioners, they're familiar with that. They're already familiar with the set of tools. So there are two things. You need to convince them that this is nothing to be scared of, that there are ways that you can actually do the right inference with this, and then you also have to provide them the right tools to do the right inference. And in some cases, it is easiest if you can build off of something they're already familiar with. That may not always be the most feasible or the best way to proceed, right? As we show, not all optimal non-private procedures can suddenly become optimal DP, under DP. Okay.
So we're sort of eating until summation.
Lunch, sorry. Okay. I'll be back in the afternoon.
More time.
So classically there is a notion of efficient estimator.
Yeah. Yes.
What do you think about like the effect of the privacy constraint of having like minimum variance unbiased sort of estimator? Do we have to sort of like give up the idea of having an efficient estimator on under differential privacy? Look for some robust type estimators.
Yeah. So,
I mean, the idea of like satisfying Cramér bounds and stuff like that.
yeah, right. Asymptotic relative efficiency and things like that. Yeah, okay, I understand what you're asking. So, you probably not going to like what I'm going to say, but I think there is value to both, right? I think it's important. For example, I'm going to go back again. We have a UMP in a binomial setting. I understand there's a paper by Kobe saying that's probably the only place you can get that such a result. I don't know. We have to do, for me, I have to do understand his paper a little bit more and then do some more analysis. So I think we should be pursuing this from both directions, right? One is that if we can get such results, such statements that you have something, the most powerful, most efficient, right, unbiased, minimum variance estimators and things like that, right? Because that means that you are adding less noise. If it's a minimum variance something, if it's unbiased, right? I know statistically what that means when I do my inference. That language means something to me. On the other hand, there's a massive literature in statistics on robust statistics, right? And there are many cases where even without privacy, we cannot achieve such results, right? So I think it's quite natural to consider situations like that as well and think about from a robust perspective. I don't know, Matthew maybe has also something more to say. He works also with more complex data, like functional data and high-dimensional cases, right?
I was thinking, so, is there a kind of concrete result that says under differential privacy you cannot have efficiency in general for like the notion of efficient estimators for finite samples? Is there kind of something like that?
I don't know.
There are results that say asymptotically, like at least under some problems, we
Adams.
Right. So
asymptotically efficient estimate.
So this UMP result that we have, that's for finite samples.
Right.
So I can't say in general it doesn't exist. So it already exists for an example, right? For one setting.
So maybe we should take this discussion offline and thank Sesha.
But these are important questions, so thank you.
We'll be back at 2.